Okay. So my name is André Tianchen. So we both work in Zürich. I'll be doing the first part of the talk, so it's going to be on transfer learning.
Yeah, I'll talk about the second part on AutoML.
So just to get an idea, how many people here have heard the term transfer learning before and have a rough idea what it is? Cool. It's a few. Maybe 15, 20%. Okay. Yep. So I'll start by briefly introduce what our team is doing, and then we'll move into the transfer learning part. And after, so we'll start by, the team introduction, then transfer learning as in like a machine learning background, and then we'll move into a project that we've been working on it called TensorFlow Hub. So it's a framework for transfer learning, and how the software challenges there help the ecosystem. So our team sits between the researchers and the product teams at Google that want to use machine learning. So these teams come to us and they say, we want to use machine learning. Sometimes we help them just by sitting for 1 hour, 2 hours, maybe like weekly with them and try to frame their machine learning problem. Other times we do education inside Google, so we are trying to ramp up all the engineers at Google into ML. And another thing that we try to do is, since we sit on this place, we see all the problems that everybody's having, and we try to come up with tools that will help scaling these, because we can't really be teaching everybody. And like classes like these are great to have, let's say, 200 people sitting here learning ML, but there is many more places to use ML, and what sort of techniques can bring us to allow everybody to use ML. One of the things that will help people using ML is, for example, decreasing the number of data samples that you need. And transfer learning is great on that side. Another thing that will help people use ML is decreasing the technical complexity of like doing machine learning, and that's where AutoML will come in. Yeah, so as I said, I'm André, working on TensorFlow Hub. The project is now open source for 9 months, and it's very much related with these. There's a TensorFlow flavor to these slides. So a quick motivation on how people come up to think about transfer learning. So this is maybe over 20 years ago, people were thinking like we need to develop machine learning that lasts like lifelong. So you want to develop agents that they just don't learn one ML task, like let me learn some regression here, and now I can predict new points on this line, but something that can acquire knowledge and evolve over time. One of the key points there is that, like we humans, when we learn a task, we leverage knowledge that we've been building since a baby. Like you spend all these years where you're doing nothing, only observing the world, and like suddenly when you have a task, you can draw all this knowledge and you can solve a new task much easier. This means that when you get a new task, I might even be able just to describe with text what the task is. And you guys have seen a lot of tasks. You know the language. You know the world around you. You can almost infer like what's to be done. So this is like the optimal way to learn. And this is sort of called like zero transfer learning or zero shot learning, where like you can go from one domain to another one. And that's because you draw on this knowledge that you have been acquiring over years and years. So how do we get there? So we'll start by reviewing like what traditional ML setup is like and how does the transfer learning ML setup is. By the way, if you guys have questions, ask in the middle of the talk. So traditional ML, you're given a data set and you're giving a task to solve, and you go and you build a model. Now you're given a new task, and you do the same thing again. And you just discard almost any information you had from before. And maybe over time, you're learning a bit like, oh, I'm dealing with images. I should use convolutional neural networks. So there's some kind of papers that come up when you solve a task. And like you're already transferring some sort of knowledge. But this is very limited. We really want to transfer much more useful information. So for example, here, if you train a model to detect triangles, and then you have a model to detect green circles, then like if you're given a new task to detect green triangles, you can almost compose the two tasks before and say like, if you see task B as like an object that's green, you could compose those two, and you almost have the knowledge needed to do your task C. So you wouldn't need to go back and explain what's the concept of a triangle versus a circle. You already have that, and maybe the concept of a color is already encoded on the task B. So we're really discarding a lot of information when we're using this traditional setup. So the transfer learning setup is you've been solving tasks, and those are called the source tasks, and you distill some knowledge out of it. Once you train, you don't just output a model to use, you have created some knowledge, and we'll go back on what kind of knowledge this can be, that you can then use later on when training a new task. And this is a setup like we'll be very interested into doing. And I think maybe drawing, are you guys familiar with multitask learning? So multitask learning is if you're given multiple tasks at the same time. So let's say you kind of skip the knowledge part and you just feed all the tasks into your model C, but you just care about the accuracy of model C. And I think there was a paper by Rich Caruana already like in '95, which was like this multitask learning setup. And he was learning how to detect if a patient had pneumonia. And he was like, just not by trying to predict just that output, but trying to predict other outputs. So for example, trying to predict the gender from the person, trying to predict if this, like which city this person lives on, or trying to predict heart rate conditions, blood pressure. I mean, once you start adding these kind of features, which they are not the thing you care about, but somehow by having them as extra tasks, they help building a representation which led to better accuracy. So that's kind of the way to do, let's say, transfer learning without having to decide how to represent knowledge. You just reuse all the tasks as a single blob, and you like train everything all the time. One issue with that is that if you want to do lifelong, like over time, you can solve all the problems over and over. It's just like, will not scale. So yeah, I already drew a bit of information on what we can transfer. Another technique that was very popular at the time is like this concept of domain adaptation. So something like, let's say I learn how to review, based on a review from students on the canteen, deciding if the food was good or bad. And then like I want to adapt this for a restaurant. And the type of language is a bit different. The type of food expectations is a bit different. But somehow the problems are so close to each other that you could almost try to reweight your examples to try to match from one domain to another. The more interesting, which is the one we're going to be speaking mostly about, is this feature representation. So when you're building a machine learning model, you have built a representation for your input. We'll go more in detail on that. This representation can be something that then you don't need to know about the input, you just need to understand this middle layer, and this allows you to reuse. So mostly we'll be looking at neural networks-based representations. There are other approaches as well, but yeah, I think these two kind of are enough. So let's start by what I mean by local representation, or by representation. I will start by distinguish a local representation from a distributed representation. So a local representation will be something that, so let's say you have a neural network, and you feed, or some sort of model, you feed all that, and then in the end you have these 4 bits. And these 4 bits encode the local representation, because if I give you just the top bit, this tells you this is a yellow circle. So you don't need to understand all the other bits. It's like just very local. Like just that thing around is, yeah. The second bit, it's a green triangle. And you don't need to look anywhere else. This is typically what we want from the output of a machine learning system. But these representations are not very robust when you try to learn new concepts. So if you need to learn a new concept, you're suddenly back at, like, I need to train one more output. And it's like, if it's just for outputs, it kind of works. But once your machine learning systems are pieces composed with each other, you now have one more dimension flying there, which means that the system on top needs to learn how to deal with these new outputs. So this is like incredibly fixed representation. It's really hard to learn new concepts. Also, like we saw, we have 4 outputs to recognize 4 concepts. And now we have like the same thing with just 2 outputs. So let's say those features now represented features that help describing the concept. So this is something that we will say it's a distributed representation, because if you just have the y1 bit, you don't know anything about what's the real object. You have some idea about the feature of it. And in this case, these outputs are like very concrete features. But in reality, this is like high-dimensional space, and 1 bit alone doesn't mean anything. So an interesting property is we have these 2 bits. We want to learn a new concept, and there was already space there. Like this combination of all these features give much more power, much more number of concepts that you can describe. Additionally, this is a lot of the motivation for neural networks and like how gradient descent can help learning, is this concept of fine-tuning. So if you have a representation, which is, let's say this is our initial representation, and now we want to learn something which is just the color concept, and we don't care so much about shapes. So we start showing our model, we start showing other shapes. And we tell it, oh, actually, this yellow circle is the same concept as this yellow square, and these 2 green objects are also kind of the same concept. So when you add a new object, you can like shift all the representations a tiny bit around, and this gives you like space to add new objects. So like over time, you can expand your model. So do people kind of understand what a representation is and local versus distributed? So we'll go a bit into a particular example. So we'll look at the image classification example. This is maybe the most popular transfer learning tutorial if you search for transfer learning. So let's say we want to build a classifier of rabbits. We have many breeds of rabbits, and we want to build that classifier. Unfortunately, I only have a limited number of rabbit pictures. Like, the amount of rabbit pictures I have, they'll not be enough to learn the concept of like edges, of like this is fur, this is background, this is water, like, and then concepts further up, like this is maybe a leg or an eye. These kind of concepts, on my smaller number of rabbit pictures, that would not be enough. So I really need to go back to transfer learning and try to learn a representation of an object that then will help me to describe a rabbit on it. So let's say if I had a representation that said it's fluffy, like it's kind of cute. Maybe I'm not very good at describing rabbit features, but yeah. So what we'll do is we're going to start with a really large data set. So we're going to have a data set. In this case, ImageNet is the popular one. So it's a data set with, it's from 2012, and there's over 1,000 different classes. So if you build a network that here at the top can recognize 1,000 classes, it's very likely that the representation you have like one step below is very good to represent 1,001 classes. This is kind of the idea on trying to reuse those representations. There's also, maybe you guys have seen some of these pictures where they grab an image classification network and they plot images where like what this layer is trying to recognize and things like this. So what you can see often is that the lower layers closer to the input, they have features like edges, points, and then yeah, you can have like describing textures and like you start going to higher level concepts. Also, kind of interesting to see as well. So we've been talking that there's this concept of a distributed representation, that a single node doesn't mean anything. And actually in the layers in between, there is this thing called co-adaptation. So for example, this layer alone maybe isn't like a very good point to cut out, because the only information we're feeding on the network is from this side and from the top. So this node might require you to look at the activations around it to have an idea of like what this representation is about. Yeah. So in our case, we don't really have so many pictures. We think our concepts are close to the top, to the output of our network. We're going to try to use one of the last layers. So we're going to use this layer as our distributed representation. The way we're going to do that is we're going to copy the network over to our new model, where we have our rabbits. And like we copy the whole network from the inputs. Like if I had copied just the layer on the top, that didn't mean much because what I was feeding was going to look like noise to it. And this is, yeah. So now we have this model, and we're just really going to learn this last layer, like the classifier on top. So you already have a feature that we think is very good, and then you could pick any classifier you guys have learned already. So let's say nearest neighbor to keep it very simple, but you could learn typically a softmax classifier on top. Yeah. So this is kind of for images, and so one thing maybe I should say as well on images, like we're saying that we're not modifying any of this network, but if you have enough data points, you could actually try to learn this classifier at the same time that you fine-tune the lower representation. So you could somehow, like the distributed representation here could start being shifted a tiny bit into small places such that you're still close to the original representation, which was something that was good to represent many objects and allows you to generalize, but like it's more adapted to your domain. So maybe like now it's not important to show textures of human buildings because you know that people are just pointing at rabbits. So that's kind of the concept of fine-tune a network. So we'll look now at maybe the second most common example. Maybe, yeah, I'm not sure which one is more common. Maybe this one is more common than the image classification one, which is the word embeddings. If people heard about word2vec, okay, this is less people than the ones that have learned about transfer learning, so kind of sounds proper, hierarchical. So word2vec, and like it's kind of interesting. Like there's this paper about word2vec, and people starting to do, you know, image2vec, which is representation of image, sentence2vec, YouTube2vec. Sorry? Yeah, channel2vec. There's like all this, and this is the concept of can I feed something as an input, and I get a vector like this distributed representation out of it. And like we saw from the ImageNet case that we need to have a lot of classes, we need to have a lot of data. So for text, this is much harder. And what we're going to do is we're going to try to come up with an unsupervised task to do it. The unsupervised tasks that people often use are like language modeling, where you try to predict the next word. The word2vec one, what they try to do is from one sentence, from one word, we're going to build a classifier that tells us the words that are nearby it. This is going to force this classifier to have a representation where words that kind of go together, so de and fox will probably be also very close because you always prefix subjects with de. So this kind of words that show up on the same context will have embeddings nearby each other because you want this classifier to generalize over this really large data set. So typically you could learn this through the whole Wikipedia. That's maybe the most common. You could try to learn it over Twitter if you want to learn a representation more suitable for this kind of data. So this is kind of important to try to transfer from the right domain. For words, like on images, we actually have something like floats coming in, and then you have maybe a convolutional neural network. But here, people could mostly get around just by having a table. So you can have almost a table where you look up a word and you find its representation. And if you think about it, this table is very flexible because, I mean, if you know that the number of words you care about is just, I don't know, the top 10,000 words on the language, you don't need to learn the model for it. You can just learn the representations for each one of them individually. So interesting things that people come up when they train these embeddings is this example where, so words have this vector representation, and what I did here is just a PCA, like bring it down to 2 dimensions. There's no random picking the seed. Like this is learned from word embeddings that are available, and just projecting it to 2 dimensions just with these words. And you can kind of see this kind of arithmetic showing up, where, for example, if you grab the vector from man to king, and you add that vector to woman, you end up on this representation space very close to the word queen. You're not going to end up there exactly, but once you try to go through your vocabulary and find all the objects that exist on my distributed representation, what's the closest one, you're likely to find a very related concept. You can also see like words get closer together because green, blue, and yellow show up on, like the context where I would see the color green is also the context where I would say the color yellow. And you can see some more like means of transportation here, some kind of, actions and other words. Go for it.
What were the 2 axes that you projected on?
So this embedding at the dimension space of 128, and then you do this principal component analysis over it, and you find just the top 2. So these are the 2 vectors that mostly represent your data and reduce the error.
Can you give me an intuition about this? Like how if you subtract king to man and you add woman, then you have queen. Like I understand the intuition behind that green, blue, and yellow have to be very close because you find them very close in a sentence. But the other one I don't understand. Like mathematically, why?
Yeah, that's a very good question, and I'll hand wave through it. I'm not sure, the main idea here is that words that often go together with their neighbors, and like once you're trying to decompose, you can see this as almost grabbing a matrix of co-occurrence and trying to find this matrix. You're trying to find representations for each side such that you can rebuild this giant matrix, but you don't need to have this n square representation matrix. You can have just the elements of it. So somehow, the sort of context where these 2 words appear, they are kind of, so you have to think that this is not actually projected onto this is projected on 2 dimensions, but the real data lives on much larger space. So somewhere there, these 2 words are nearby each other because queen and king happen, I don't know, text from the kings and queens times. And these 2 words show up on a different type of context. So they'll be kind of close to each other on this context. And then if you imagine one dimension is this context, the other dimension is gender, and somehow when you project back on this, you end up finding these nearest neighbors. So you kind of need to imagine that there is, infinite number of contexts superposed on these dimensions, and these kind of properties emerge. I think, when this came up with, it's kind of surprising that it works as well as it does. So if we want to do text classification, so we could learn these word embeddings going through a really large corpus. And now we have representations, for example, king and queen are nearby each other. And now we're going to reuse those representations. When we see words, we're not going to use the word as an input to our model. We're going to use this representation. And this will allow, for example, if you learn that king and queen are things that somehow make our sentence positive, we could imagine that princess, because princess and prince will be very much on the same space, will be close on the representation space. They also mean the same thing. So we're kind of relying on this representation to cluster terms together. And we're going to use that knowledge. So interesting here is that on the other one, we're almost reusing the full model that was originally built for image classification. Now we're reusing it, just cutting a bit and adding on top. Here we have a slightly different setup. The way we learn these word embeddings is unsupervised learning for it, completely unrelated with maybe the set of techniques that we're going to use to combine all these words and come up with a classification to our sentence. Yeah. So some warning. So yeah, one thing, like, it's not like, oh, I'm just going to use transfer learning and problem solved. Actually, it's not even like I'm going to use machine learning and problem solved. Sometimes you have to go one step back and think, is machine learning like the right tool here? First one, and then like the thing I'm solving, is it really the problem I have? And what we're seeing is that sometimes people are using it without considering like where the data comes from, in what kind of scenarios this system is going to be used. And we're starting to see a lot of concerns for bias and fairness. And I think there is this paper title that describes these concerns very well. So, man is the computer programmer as human is the law maker. If we reuse these embeddings over and over, we're just going to be reinforcing this bias that were already in the data. So I think this is a general caveat, not only for transfer learning, but maybe here, as we're helping, like if the person that built the original transfer learning model now gets used by 1,000 people, well, maybe there's more responsibility there on like, so I'm especially raising a point here. Another thing about transfer learning is that when you're transferring something, it's not like, it's actually hard to predict the performance, and it's very hard to predict how good you think it will be, like did you do any mistake in the middle? So like finding the right domain from where you're transferring is kind of important. And there is this concept of when you transfer, you kind of get a bad transfer, your model performance goes lower than if you had not used this transfer learning. And like you can imagine if I give you a representation that was, let's say, color agnostic, because I built a shape detector, and this shape detector never needed to learn color. So my representation just doesn't have that concept. You'll be much better feeding raw pixels in if you wanted to build a color detector. So it's like a very simple approach, like explanation for it. So you have to be careful where you're transferring from, and considering from which domains the data is coming from. So these are maybe the main reference if you guys are more interested in learning about it. Some of these are kind of old, particularly these distributed representations. This survey on transfer learning is a bit outdated, I think 2007. This one, distributed representations, is from Jeffrey Hinton. And it's like laying out a lot of why does a representation on neural networks kind of work. So it explains these concepts of when you have the distributed representation, you add a new node, things can shift a bit, and why there's more expressive power than having these local representations. This is the Word2Vec paper. This paper here, how transferable are features in deep neural networks, is something that train image models and try to find what's the best layer to transfer, like a lower layer. Is it better to transfer from a lower layer, from a middle layer, from a higher layer? And it shows like problems with bad transfer, bad adaptation to new problems. It's kind of interesting. And the last one is a pointer to many things about fairness. And with that, I'll move into the next topic. Yeah. So my main software project is TensorFlow Hub. So we use a lot of TensorFlow, and we're seeing a lot of teams coming to us that they want to train ML models. What we see is often these people don't even have the data, and there's some other team at Google that has that data, and is like, how can we help these teams, like sharing between each other, like leveraging all this training that happens in one side to the other one. And we see this also externally. So what we're seeing is that it's not enough to have there the papers and knowing like what to copy or network. In reality, this is much harder to do, and like finding the right model is really hard. So we're seeing that getting the right software concepts can really speed up this a lot. So the main question we had is, how do we make transfer learning, like these concepts of a piece that you copy from one place for another, like very easy to consume? So let's see what you'll do nowadays if you wanted to do transfer learning. You find the code that represents the architecture, and you find the weights that were trained with it. Then you try to use that code, and then you find you don't have the same Python version, you don't have somehow the same libraries, you iterate over it. And then you try to use the weights, and you find that you don't even know how to use that code because you don't know which hyperparameters were used by the original person. So like there's a lot of manually plugging around. Once you think you got everything, then you have to find out to integrate that with your project. And then you get bad performance, and you either blame it on bad transfer learning, you just go back and try to debug until you think you know the reason why it's performing bad or performing so good. Sometimes the reason it's performing good is because you were feeding the wrong data. So a lot of these steps are very common to reproduce ML, and we're trying to look at like how can software help this. So I'm going to give you a bit introduction of TensorFlow. How many of you have used TensorFlow? Okay, that's maybe the first question. I got more people raising arms. Good. So if you look at when TensorFlow was created, by the way, I'll justify a bit why there is all this concept of graphs and why people bash their heads a bit against it. So if you go back when people were doing deep learning and TensorFlow came out, having large amounts of data was important. If you wanted to build a cat detector from YouTube videos, you're going to feed loads of data on it. The set of techniques has improved where we can almost train this on a single machine with GPUs. But at the time, you needed to feed loads of data. You needed to go distributed. And people were like, there was papers coming out, oh, I have a new algorithm to train really fast. It requires you to run this code on a server, this code in this many workers, on a distributed data center. It was very hard to develop algorithms when you had to touch software and distribute it across all these machines. So the concept there was we can have a language that describes a graph of computations, and now we can ask this computation to be distributed. This allowed you to write your program to train on a single machine and allow people to develop networks and optimizers and and even distribution techniques all on the same language without having to think about going to the network protocols and passing bytes around. The cool thing is once you have this graph representation, you can now get something that grabs this graph representation, runs it on GPU or on CPU or on the distributed machines, as many machines as you want. You can also do automatic differentiation, which I guess you guys might have done some differentiation by hand, maybe as an exercise. So that's kind of gone. Nobody really does that, only for introduction courses. And then there's some nodes on your graph that contain the weights that you train. So this representation is kind of code independent. So you can write a complex program that the output of it's a graph. And that's kind of an interesting property because this allows us to decouple the code that trained your model. Might be some code that can only run on your machine. Its output is a graph and some weights that you have trained, which means that if someone can use that graph, they don't even need to use your code. So like a lot of the problems that we're pointing out when you try to use transfer learning, they could be gone if you can use this intermediate representation. And that's kind of what we did. We packaged, instead of sharing ML as sharing code and checkpoints and teaching people how to link libraries together, we're like, this is an intermediate representation. It's like a library. We added a few more things like hermetic inversion because we got a lot of pain points when we try to do things in production where models change under your feet and you don't understand why your model just failed because someone pushed the improved version. This happens. And hermetic, like just to make sure your system doesn't depend on other pieces that just go offline. So this is kind of the concept. I mean, I'm explaining this concept as very much TensorFlow related, but the main goal here is like there's this software constructs that really speed up a lot, and this concept of a module, like something that you bring from an ML model into some other system. So you can see that producing a module for transfer learning is just not about I'm going to train it and it's done. That's one approach to it, but if you produce a module like that, maybe it's not so usable as if you had produced a model that you intended originally to be transfer learned. So like maybe you should try to increase, maybe you'll go for unsupervised algorithms because then you can feed more data through it. And now you can spend more compute power on your side such that you end up with a better representation. So if you're on this side where you're trying to produce a module to be usable for transfer learning, the set of techniques that you use are very different from the knowledge that you use when you're building a full model. So once you have this module, which is code independent, you can push into a repository, and someone that wants to use it, they can go to the repository and they can find out all these modules there. Another interesting thing is if you make the interface on this library kind of swappable, you can allow people to try out many embeddings. And we're seeing a lot of papers where, I mean, to advance the state of the art, people need to sit down and write benchmarks that compare all the modules produced by people so that we have a consistent view over it. It's not very useful to read, I beat the state of the art, but I cleaned the data set a tiny bit before, or I did like some other technique on it, or like I use a different data set because I need access to yours. So like this kind of helps a bit on the people to evaluate representations from each other. It doesn't solve all the reproducibility part of ML, but like being able to reuse artifacts that someone produced is kind of a good step towards that. Yeah, so where to slice? So if you're creating this kind of modules, a question is like, do you want to share word embeddings or do you want to share text embeddings? And the difference here is, for example, if you have a word embedding, that'll be something you give it a word and it gives you a representation. And that's pretty good until you hit a language like Chinese where you can split words in spaces, where now the kind of concepts are a bit different. So maybe to be used by a larger number of ML practitioners, what we want to produce is something that you give it a sentence, let's say 1 or 2 sentences, the sort of tweet size, and it produces some kind of embedding for it. This is like maybe a more interesting way to slice the thing you want to share. And this allows people to swap things fast. So the library we did, we kind of ended up trimming it down to 2 lines because we also built in the fetching modules out of it. So it's like just defining the module that I want and then trying to use it. And now I'm plugging a classifier on top of it. So I'm plugging a fully connected layer with a softmax classifier. This is our rabbit example before. So we really tried to make it very easy to use because, as we're pointing out, our main goal is increasing adoption of machine learning. More people can do ML. We got a lot of text modules available. And I mean, you can produce your own. I think the interesting thing here is also to know what kind of embeddings exist. So for example, neural network language models, this is from one word you plug, or from a context of words before, you plug 1 or 2 layers of neural network and you try to predict the word after. This creates a set of embeddings. The word-to-vec embeddings were the ones we just saw. These ELMO embeddings are interesting in that they actually take, they're more like up-to-date techniques. So they grab a word, they split it into many characters, and they produce some kind of embedding, which is character-based, and they also use a word-based embedding. And then on top, they plug this thing called bidirectional LSTM, which is something that goes through your sentence on kind of both directions. And this allows you to somehow learn not something or this word refers to that word. So it allows you to build kind of better representations. And this universal sentence encoder, it comes from the field of actually to build better representations. It's not just about the number of data points we have from Wikipedia. We should actually be feeding multiple data sets on it because different data sets kind of have different domains of text and they care about different properties. So they end up with a very good generic embedding for many tasks. For image modules, we have quite a few of them. And these ones are the most classic old ones. And now we're seeing kind of a more trend with some of these, the NASNet and AmoebaNet. So AmoebaNet is the architecture. Tianchen will talk more about that. So this goes very much into the AutoML, where we're using other techniques to produce the modules. iNaturalist is also, most of these have been trained on ImageNet. iNaturalist has been trained on a data set just based on images from nature. So you can imagine the set of features it's ready to describe is a bit different. So if you wanted to detect more like, human objects on daily life, maybe that's not your best choice. But if you're building a rabbit breed classifier, that's probably a better starting point. There's also other things that we can transfer, like I just touched these 2 examples, but you can transfer representations of more things. DeepMind has this very interesting action classifier. So they have a data set with loads and loads of actions. I think is like videos from YouTube, like 15 seconds. And if you feed this through the model, with all the frames, it will say, yeah, people playing cricket. So it's kind of interesting because most people will not even know how to feed video on their neural network. They'll not have the data and the compute power to train it. But you can feed your video through this representation layer, this module, and you get this representation that's maybe it's good for. So it has actions like cooking. I'm a fan of outdoors, climbing, and so on. So it knows how to rappel and distinguish rappel from climbing and other kind of actions. I think it has over 400 or 600 actions. This is a module that, given an image, can like give you already objects. And this, you can see this is already a bit more like a local representation of it. So like when you fit this in, you're going to get a lot of bounding boxes. This is a progressive GAN. So this is so GANs are also very, very interesting to learn representations. And yeah, so I think we're just starting to see that field, but this will be very interesting. And Delph is, maybe you guys had some more computer vision lectures before. So like people used to build all these point descriptors, and that helps you to find 2 images and try to find how much they are rotated between each other or detecting objects. And what we're seeing is instead of handcrafting those features, people are using neural networks to describe those features. So this is very interesting line as well. So you can try it. Like all these TF modules, they kind of come with a Colab on it, so like a notebook. Yeah. So it's there again. So just to end, there are more cases of reusable ML. I think we talk about transfer learning, and now then we try to make reusing machine learning easier, and now we're seeing a lot of use cases. But you might have heard about this concept of ensemble. So like you train a bunch of different models, and then you can take, let's say, a vote of it. And this model will, almost all the competitions, the best model is always an ensemble. Is like, yeah, I think that's how almost always the case. Distillation is also a very interesting concept showing up over the last 2 years maybe, where you train a model, and then this model might be really hard to use, so you're going to learn a new model based on it. Surprising, you can make this model smaller, you can make it better accuracy. It's kind of being used to learn something on a machine and then like on a desktop and then trim it down to run on mobile is a very common use case, but there are more use cases for it. Data augmentation is also, a lot of data augmentation is very manual at the moment. So you really have people coming up with, I want to detect text, so I can rotate a bit, but I can't really flip it back and forward. And if I want to learn images, I can flip it. But if I want to detect humans, I should not like change the colors around because suddenly the things are not the same. There's like a lot of this data augmentation is very manual at the moment, and there's kind of these things about can we learn augmentation techniques. Architecture search, also very related with AutoML, and even the concept of evaluating other people's code like on a fast way. So like, so I think that the main thing is like we're really finding that ML, the kind of software we use for it is kind of slowing us down a bit, and we'd like to have more systems that are designed to be decoupled and like plug and play pieces. Because it's very nice when you have a paper and it's like, oh, this is the diagram of my network. It's like, oh, this is actually like a big program that it's hard for you to modify. Yeah, I think I'm done. So questions?
competition afterwards?
Yeah, we are trying to find that out. Maybe. It's on our to-do list. Was there any particular links? Like, do you want to get the references? I don't know. So, I mean, they are recording as well, so. Okay.
Okay, so